It says live. I see only 2 viewers, 5 viewers.
Okay, looks good.
Okay. There are 7 viewers. I'll just hang on for a minute or two while people come on. Greetings, everybody. We'll just give it a minute. I see the count of viewers going up, so if you can hang on for a minute while people connect. The viewer count is still going up, so we'll hang on for a minute or two. Okay, let's get started. I think most of you know me. I'm Rajesh Bhaskaran, and I teach engineering simulations at Cornell University. And I've been working with different courses, and it occurred to me that I could, with online learning and with the MOOC movement, I could put content from different courses together, and in the process create a new kind of a course where simulation is fully integrated. So I think it was very satisfying creating this course for me, and seeing people's responses in the sense of in this course overlays fundamentals, practical skills in ANSYS, as well as industrial applications, and it's all stacked together into one piece. And usually these are all kind of separated out. And also by using a tool, a powerful tool such as ANSYS, one can go across different fields and areas and kind of get kind of an integrated view of the entire thing, which is again what the technology kind of allows you to do. So today I have with me two people from industry who are really they're my dream team of FE analysts in industry. We have Andy. Unfortunately, Andy has been having some problems with his video and audio, so I have him here on speakerphone, and he'll be responding, via the phone, and hopefully you'll be able to hear him. And Andy, as most of you know, created the model that became the basis for Module 3. And I talked to Andy and our other guest, Sean, about what is like the most common application of FEA, and I think the response I got was bolted flanges. And so Module 3 shows you one of the most common applications of FEA. And I think I have Andy's camera feed now. Maybe this will work. Andy, can you hear us?
Yes, I can hear you. Can you hear me?
Okay, let me turn off the speakerphone.
Okay.
Yes, we can hear you.
Okay, great.
Okay.
right on time.
Perfect. And I have the other, distinguished guest we have is Sean Harvey from ANSYS, and Sean has been giving us, just fantastic help on using ANSYS. And when we see, when we have calls with Sean and he's showing us things, in fact, he showed us some tricks on the bolted flange too. How do you get like a pure hex mesh and so on? So Sean is a real whiz with ANSYS Mechanical, and in fact he's traveling in India. But these days it's pretty amazing that even though he's on travel across the pond to the other side of the planet, we can still have a conversation with him. So it's a real kind of pleasure to have both of them. And then last but not the least, I also have Julio here, and Julio might be familiar to you from the discussion board, and I've been very dependent on him to run the MOOC in terms of reviewing the content and staffing the discussion boards and so on. And so Julio, is going to provide us with the student perspective here, and he's also going to help us kind of sort through the questions. So I want to, and Julio, by the way, is actually a visiting student. He's an exchange student from Brazil, and so I'm very glad that I was able to connect to him during his relatively short tenure at Cornell. So I want to start with Andy. And Andy, do you want to start by describing, I think people are interested in, it's like in your work at SpaceX, right? You're doing lots of different things. So if you want to give us an idea of, the kinds of things that you do and the role that simulation plays in it. And maybe some of your own background, how you got into this position.
Sure thing. So I started off in mechanical engineering, and I didn't really know what I wanted to do. So I ended up working at Procter & Gamble designing toothbrushes. And then I decided that I really wanted to do something that involved all of humanity. So I wanted to get into aerospace. So then I got my graduate degree in aerospace, and then it just happened that SpaceX was hiring, so then I joined in. In terms of simulation, or in terms of the vehicle, so SpaceX designs the entire vehicle, like the rocket, the engines, the place where the like the command module where the astronauts and/or payload go. And then what simulation does for us is that it can tell us whether or not designs will work or not, or how they can better work and how they can survive longer so we can reuse them before we actually make them. So, so for example, if one wants to design a beam in bending and it needs to handle a certain amount of load, yet not deflect too much. So there's that simple equation, FL cubed over 3EI, which somebody came up with, like a few hundred years ago, and it works really well. So for SpaceX, we do that, except finite element analysis is used quite a bit in order to help us get there.
Okay. And Sean, do you want to talk a little bit about what you do at ANSYS and the kinds of analysis you're helping customers with?
Sure, I'd be glad to. So my name is Sean Harvey. I'm a lead technical service engineer and manager at ANSYS, and I have a team, a small team here in India and a team in North America that does what we call technical support of the ANSYS mechanical product. So essentially on a daily basis, we get calls from customers, and we help the customers not only answer their questions, but solve their simulation, needs. So, not often just a simple question evolves into something that is quite elaborate. Usually, a company has a product they're developing, or they have a problem, and they'd like to better understand it, and we essentially help them get there.
Okay. And what are, you said like the bolted flange, for instance, was a very common example. What are the kinds of applications that you see that people are using ANSYS for in industry? Are there some predominant ones, or is it like pretty spread out across various industries? And do you see like a change over the years?
Oh, absolutely. Okay, so I've been using ANSYS for 26 years, and 26 years ago you could do something very small, something very simple, and nowadays it is not uncommon to have full system level models. So last night we had a call from General Electric Engines, and they have an entire turbine engine modeled in ANSYS, and they're looking for natural frequencies of one particular component. So they're extracting, 4,000 natural frequencies and having to go through a ginormous model. So we have customers that use it for simple things like, electrical connector, working with GE on an electrical connector where it heats up because there's voltage, to things like wind turbine blades, to the iPhone that's in your pocket, or the Android phone or the Microsoft phone that's in your pocket. But some of the other interesting customers too is like the family of Elon Musk and the Tesla. They're our customer. So we have customers. That's the beauty of ANSYS, is that it's the general purpose finite element solver. And again, I'm just specifically commenting right now on the mechanical side, but we do the full electromagnetics and the fluid dynamics and the structural mechanics. So we see the entire industry. We've got iRobot that makes a little Roomba vacuum that will clean your floors. They're our customer. And Cummins makes engines and generators, and Firefly. I shouldn't say Firefly in the presence of SpaceX, but they make rockets too, just like SpaceX. So our customer base is very diverse and very varied. And one thing I will comment is that the complexity of models has grown astronomically, to the point where we're able to solve in the hundreds of millions, if not soon to be multiple billions of degrees of freedom systems.
And for that you use, like what kinds of computers do you run these massive models on?
Yeah, so typically those big models will be run on very large clusters. When we're talking billions of degrees of freedom, those are benchmark models. A typical customer will be running in the hundreds of thousands of degrees of freedom, but most engineering structures can be done in the thousands of degrees of freedom. So a lot of times going simpler is better, and I think Andy may comment on it as well. But getting to your question, Rajesh, it's not uncommon for people to do actually a lot of work on their laptop. I have many customers who are doing very large assemblies right on a laptop, a high-performance laptop. But the bigger stuff is done on the cluster with usually 48 cores and 512 gigabytes of RAM. That's a pretty typical cluster for a large model.
Okay. Let me go to the first question. This is a question that's been voted up by other viewers, and I think a lot of people are trying to figure out. And in fact, I get these questions from Cornell students too. It's like, if you want a career, doing finite element analysis, and this particular question from Utkarsh is in the automotive sector. But generally, in terms of if you want to make a career out of this, there are two ways you can use simulation, right? And I was mentioning this to Andy yesterday. One is you can use it as a tool in your tool set. That you're working on some design and so on. You do your hand calculations. You refine your design using simulations. So they're using you're a general purpose engineer using simulation as a tool. The other is you specialize in simulations. Otherwise, you specialize. You can specialize in simulations, and you become like a finite element analysis expert. So let's talk about that first. If you want to, if this area speaks to you, and if you want to go into finite element analysis, how do you, first of all, how do you kind of build up your skills, and how do you make a career out of it? And Sean has definitely done that, but he has a long trajectory. But you want to give us some insights, both Sean and Andy, on that. And let me start with Andy.
Sure. So what I would say is it's important to realize that when it comes to analysis, all analysis all analyses are wrong. Some are useful. So approximations are made to get as close to the final answer as possible. In fact, if one does an experiment, one could say that all experiments are wrong, some are useful, because it takes a lot of experimentation, because you're going to get variability to get the right answer. That's why when tensile tests are performed, you have many samples, because you're going to get a normal distribution or some other type of distribution. So in terms of like a career in simulation, if you like analysis, typically, like if you do really well in your theoretical classes, then analysis may be a really good fit for you. But I do see people in industry that do analysis and design and test engineering, because there's a need to have the ability to do all of that. For me, I'm most interested in physics, so I spend most of my time in that. And then in order to do that, there are some like fundamental equations that describe beam bending or frequency, like drum frequencies or other things. And then what I do is, if I have a complicated model or even a simple model, if I'm new to that particular concept, I will actually create a finite element model of a simplified geometry from Rourke's handbook or some other structural handbook, where I model what they've shown in the book, and then I show that I get the same frequencies, and if I do, great, like I understand what's going on. And then I also have an Excel calculator where I can vary small parameters and get very quick ideas on how things change. For example, does changing the thickness by 10% cause a 33% change in the final outcome, or is it 20%, or is it only 10%? So like knowing where you put your money to see it grow the most in the design is important. Like meaning knowing where the biggest knobs are. So I actually have a collection of about 20 to 30 or 40 small analyses that I use to anchor those cases, and that's how I build my understanding of that. And then when I build bigger models, I could refer back to these other Excel sheets or these other kind of math models that I built to verify what I've had. And then I would say if you enjoy doing that, analysis is maybe your path. If you don't, maybe not.
Okay. And so basically you need to be able to do the hand calcs and understand the theory well, but it's also very useful to know ANSYS really well, and to kind of go between the two.
Yeah. There is a book called Outliers. It talks about 10,000 hours, and I thought there were some good points in the book, where if you want to become a chess master, you play for approximately 10,000 hours. Same thing with piano players. And so when it comes to FEA, if you're working many hours a week, then maybe that's only 3.5 hours of work for you to get to that stage. But it really just takes a lot of going here and there and over here, and not focusing on doing the same problem over and over again. Just kind of like pushing the box a little bit more to really understand what's going on with the physics. I think that's important.
Okay. Thanks, Andy. And let me turn it over to Sean in terms of, okay, you want to make a career out of this. Or,
right.
You're hiring people, right? And
right.
So what kind of credentials are you looking for? And what do you see as the opportunities going forward? It's like, I really enjoy finite element analysis, and I really enjoy, let's say I really enjoy working with ANSYS, which is true for me. And it's like, okay, is this something that I should do as a hobby, or maybe I can make a career out of it?
Right. Well, thanks. That's a great question.
To build.
So, Yeah, so one thing is, we find is it's great to have a good, strong fundamental background, a theoretical background, right? So we gain that through the course and the coursework so that you understand what's going on behind the scenes. Because the biggest danger with finite elements is that, you're producing, like Andy says, it's incorrect. And it's an approximation. So understanding what's going on behind the scenes is critical. So what I would say is, make sure your fundamental skills are very good. It's not just about pushing buttons. It's about really understanding, what's going on. And I would say, it's a great time now to have a product like, the ANSYS student product, because you can do so much to build your skills to try and enter into the market. Okay, with having the time to utilize that product, and I would say don't be afraid to try and learn, and you can't break it, and so you can do exactly like Andy says, and I agree 100%, is you really start to gain confidence in the tool and your work when you start comparing theoretical with experimental and simulation. When three of those come together, you really feel comfortable that you know what you're talking about. I can recall many cases when I was working at United Technologies, Sikorsky Aircraft, designing rotor blades and rotor blade components that you would do a finite element analysis, but you really wouldn't know if it was correct, okay? And some people don't have the luxury to actually do the testing, but I had the luxury to actually go down and do the testing. And when you can pair those two together and see that your model and your testing were within, less than 10%, which, we're never going to we get customers who want really, 1%, but realistically, you're looking between 5 and 10%. When you get that, you gain a very strong, confidence in your tool. But, getting back, like I would just say, work on your skill set of using the tool. But in addition, don't be so focused that it's just simulation, because an engineer that would be a well-valued engineer at ANSYS, or a company that's going to use simulation, is going to look for someone who can have obviously critical thinking skills, understand a little bit of business, communication skills, the intangible skills. So we particularly look for well-rounded individuals, but we're also on technical support. So we're interacting with the customers. But from a technical standpoint, I would just say brush up on the fundamentals, make sure you have a strong understanding of the fundamentals, and then try and model things that you find interesting. And if at the end of the day you find it still exciting, then yeah, it might be a good career for you.
And do you see opportunities growing in this area? Do you see companies? My sense is that working with I'm in university, I'm kind of sheltered from the real world, but my sense is working with this is like very, very powerful. Of course, it's very critical. If you want to, a student is asking, how do I become like Andy, or how do I become like Sean? Yeah, you have to know the tool well, but you also need to have the theoretical background and go between the two. But do you see? And to me, from in academia, it seems like this has only got to grow because of the power of it. So is this? Do you see, and Andy can also chime in, do you see opportunities growing in this area or not?
We do. I'll just chime in and I can pass it back over to Andy. But the FEA really got its original applications in aerospace, and then it has branched out to pretty much all industries. And the last industry really to adopt it has been more the healthcare biomedical industry. So 15 plus years ago, very little simulation done in biomedical engineering, and nowadays you cannot design a part that will be implanted in the human body without going through some form of simulation. So it is definitely growing. I can tell you that because our customers are increasing and the questions we're getting are increasing. So yeah, it's definitely a growing field, and it has been for some time.
So biomedical is obviously a big one, and it's a huge. And do you see that internationally, or is that, I know in the US that's the case. Do you see that internationally too?
Oh, we do.
The biomedical, the growth in biomedical, the simulations in biomedical?
Yeah, absolutely. We have offices in Europe, and I see the work that's being done over there on biomedical, and work with the universities. So all kinds of products, but it's not just the biomedical. It's the aerospace, the auto sector, the oil and gas. Oil and gas has actually had a downturn, right? But so their industry is the one that's suffering currently right now. but the other industries, are pretty robust.
Okay. What about you, Andy? Any
Yeah,
like the future opportunities in this area and having these kinds of skills?
absolutely. So the way I look at it is that, maybe 20 years ago, every few people had Excel on their computer. Now everybody has Excel on their computer, and a lot of people use it for various purposes. So I think in the future, almost everybody, instead of just a few people, will have simulation ready on their computer. So like at a lot of engineering companies, you have CAD programs already installed because that's how you check the hardware. And then inspect it. So when it comes to analysis, I kind of see it happening on everybody's computer because people are learning it more and more in school. And if they're not, they're just learning it when they come out to kind of keep up. And as it's becoming easier to use, and people are getting more familiar with it, yeah, I think it's going to be continuing to grow up among not only everybody's computers but also into these other industries that Sean was mentioning.
Mm-hmm. Let me go to this question. So let me read the question from Varun. As a part of design requirement using CFD for aircraft wing, how much tolerance is allowed between experiment and CFD modeling? And second, how much does simulation reduce in the development phase of design? And we are in this case, I have two, experts on the FEA side. You don't do much CFD, right, Andy, or do you do CFD also?
I do some of it as well, so I can roughly answer the question.
Yeah, but I think this question also applies, in the FEA, right? How much it's like you have these three things: you have hand calculations, and you have the simulation, and then you have the experiment. And how, what is the role of the experiment? And I know like CEOs, right, want to eliminate experiments altogether. So what do you see as the role of the experiments, and how that is changing? And second is, how does and what implications it has in terms of the development time for design, bringing design to market.
Right. So I think that, and this is kind of jumping forward to another question that I saw on the list, is experiment will probably always be needed. It can be reduced over time with analysis. It's kind of like me going to my sister when I was a kid saying, you think Dad will buy me a train? And then she'll just say, well, why don't you go ask him? I don't know. So like, she's my simulator because she's older and she's smarter. And then my dad is like the ultimate experiment. I mean, he's a little, I don't want to say unpredictable, but there's a lot more things going on depending on the budget for the year. So so I would say that experiments always is always needed. However, it's being reduced further and further each year with analysis because it's just cheaper to do analysis. And if you do an experiment, let's say it's a rocket engine, it's very difficult to test all of the cases in a given experiment because of cost or because of of the time available. But with analysis, you can cover all of those boxes pretty quickly. So there's many corners of the box. So for example, variations in temperature, pressure, fluid density, etc. And then what was the question again?
It's basically, experiment versus simulation.
Oh,
What's the role? And the second is like what kind of effect it has on your, on the development, right? I mean, we always hear like people talking about how simulation reduces the, the design to market kind of cycle.
Yes.
And so what's your own kind of experience with that?
Right. Okay. So when it comes to CFD, I would say with some, like I used to do toothpaste simulation with Fluent back in the day. And then when it came to certain delta pressures across this toothpaste tube that we were designing, we would expect it to be within like 10%, and that was good. Because the consumer doesn't really, their tolerance is much greater than that, like maybe 30, 40%. So when it comes to fluid flow, I would say within 10 to 20% is acceptable. And then when it comes to structures, I would say that nailing the natural frequency to within, say, 20% is good, 10% is excellent. The hardest part is like the joints in the system. So if you have a bolted assembly, it's very difficult to capture that stiffness accurately in a finite element model. Whereas if you just have like a pure beam, you should be able to nail it like within like a percent. I would think maybe 5%. I would say within CFD, within 20% is great. And then within structural, within 10% is really good, maybe 20%, because if you take if you're in aerospace, then you use A basis properties, which is like the bottom 3 sigma of the properties that you would expect to get. So if you have like a barrel of 100 volts, A basis would be like the bottom, you would use like the lowest value out of that 100 in tensile testing. So if you were to do like FEA, and then that FEA using those A basis properties may predict that the structure can handle, say, 100,000 pounds. In reality, you push the test to failure, and you may find that it can go to 120,000 pounds. That's typical, where we see that 20% variation, where the structure is able to actually go 20% higher, because you're only as good as the inputs that you put in, whether that be material properties or how accurately one is capturing the joints at the bolts. Now, for the second question regarding how does a simulation tie in with getting things to the market quicker, examples would be saying, yeah, we did 147,000 pounds of thrust with the engine. Analysis says that we can go a little bit more. And then then that goes over to the testing arena, and then we start pushing it more because we see that we have a little bit more capability. Or it could come in that we have like a very complicated bracket design, and it's expensive, and we want to go towards a sheet bracket. So a designer can draft something up. Often the designers here do analysis as well. So they'll do the quick analysis and say, hey, I think this will work, and they'll pass it over to somebody like me, and then I'll put it through like a lot more to take into account thermal loading and then acceleration loading and all the other stuff that I can simulate with it to model the dynamics and experiences of launch, and then we can say, yeah, this is a cheaper solution, let's put it out, and that can happen within a day, and then it's a good cost savings.
Okay, let's move on. So I'll try to get to quite a few of the questions that we have. This is from Sean Lippy, who has actually been, he's one of our communities, and he's been just fantastic on the discussion board. So thank you, Sean. And Sean's question is, are there any common repositories of experimental data we can use for validation purposes on models that are commonly used for mastering simulation techniques? And for example, University of California at Irvine has a repository for machine learning, and it got cut off there. So do we, in, say, structural analysis, do we have repositories of experimental data that one can go to? And let's start with Sean. Let me give Sean a...
Sure, Rajesh. So, I'm going to take it in the context of material data, and maybe it's not the actual question that's being asked. There are.
It's like, are you aware of like repositories of experimental data for materials? Definitely, that's so critical.
Right.
We have a company in Ithaca that Point Labs.
Data Point Labs. Right.
The bike crank model, and they basically give you the test of material and give you the material properties to put into the simulation. So you can talk about material properties, but also any others if you're aware, or they don't exist.
Yeah, I mean, material properties, there are companies out there. It's not hard to find. There's MatWeb, and there's Data Point Labs, and there's Axle Testing Labs, and now I won't focus just on materials, but there's lots of companies out there that you can gather information. In fact, you can go to 3M's website, or you can go to, if you're in composites world like I am, you can go to Hexcel's website and download data sheets of actual materials. You know, these are going to be non-proprietary materials, but many of the non-proprietary materials are freely available. So you can find lots of data. I know in like the ANSYS student version, you're just going to see, you know, a small subset of generic materials. But online, there is quite a bit of materials, data available. There used to be a reference I had when I was at UTC called the Aerospace Metals Handbook. It was a wonderful reference, and you could pick a metal, and it would have everything you wanted to know about the metal. Well, more than, you know, there's another reference for metals is the Mill Handbook, what used to be Mill Handbook 5, and it's called what, MMPDS, and those all have very good references for actual materials. So, and typically, I'll tell you, if we're going to, I may diverge a little bit on that topic, but the biggest challenge, the biggest challenge in FEA, I will tell you this, is getting the right materials. It's easy to get, we all know Young's modulus of steel and aluminum, and that's easy. We know Poisson's ratio. But when you start getting into things like large strain plasticity and hyperelasticity of seals and temperature dependent and viscoelasticity, those are the areas where you know, Andy and I would say if you're within 10%, great, but you're probably going to be, you know, beyond that, and you should be ready to accept that. But yeah, I think it's great if you can you know, extract material data, you know, freely and use it and compare it with some experiments. You're going to learn a lot about the simulation that way.
Okay. What about hand calcs? You know, are there? I guess you Andy referred to Rourke and so on.
Yeah.
By the way, you know, there was a question whether the Hangout is being recorded. Yes, we'll make the recording available, and also what we will do is we will make a list of the material repositories that Sean mentioned, and we'll put it on that page so that, you know, you can access that information there. So the Hangout is recorded, and we'll also put the links to the material data that you can use, which is very important in simulation, on that page. So you can go and look at the repositories that Sean mentioned. And I forgot, Sean, what were you? Where were we at? Do you want to say something else? I don't know. Did Andy had something? I guess let's. Oh no, yeah, you were sorry. Yeah, let's go to Andy in terms of repository of hand calcs. In fact, it occurs to me that it's very useful if we had like an online repository of like hand calcs, which is, again, you know, one shouldn't use these as, I've seen students, it's like, okay, here's a formula that I can plug in, right? My by I, sigma equals my by I. And you have to really understand, it's like, what is the physical principle on which it's based, and what are the assumptions based? Okay, and are those assumptions valid in my model? And so, you know, one has to really kind of, the formulas are useful, but one has to really understand where those formulas come from. But given that, I think it would be really useful to have like an online repository of like common hand calculations that are useful for FEA and for CFD. But I'm not aware of anything like that. Andy, are you? But there are books, right, that one can turn to.
So like a couple of ideas. One is when it comes to data on failure types. There's definitely the material data. I don't know if I've seen like a library of that for structural, like you know, statics. I have seen it for buckling. So there's the buckling handbook. It's like an 800-page book full of different buckling experiments, and it'll show different geometries. There's also NASA SP 8032, I believe, and that's buckling of doubly thin curved shells, so like spheres or cylinders. If you search for NASA-SP, they probably have a library where they compiled the stuff back in the 60s when computing power wasn't super high, but they came up with like a bunch of fitting factors or knockdown factors to take into account real structure versus theoretical structure. So if you were to look at buckling for a sphere, you could get the theoretical result. However, in reality, there are perturbations in the structure because nothing is ever exactly smooth. and those NASA SP documents kind of cover some of that, which is really helpful. And I've compared that with ANSYS, and they match to within 1%. So, and like, the ANSYS simulation for me took a while, and I needed it because I had more complicated geometry. However, for like a pure spherical shape, for some of the tanks that I worked on, it matched ANSYS within 1%, which is really cool.
Okay.
And then, okay, and I was going to comment on one other thing. Is like in terms of calculators, I just make my own because that's a good way to learn. I have like over 100 calculators I've built. I'll make a new one every week or something like that.
And this is in Excel?
Yeah, in Excel. I use Excel, and then so I'll have a bunch of calculators, and sometimes I share them. So I have one for bolts. I have one for pressure drop across a pipe. I have one for pressure drop across a sharp orifice. It goes through the CD and Reynolds number. You can calculate all that. One for transient heat transfer, and then I used ANSYS to validate the spreadsheet because I did that derivation where you do like I plus 1, etc. And then I used ANSYS transient to validate that. And then with that calculator, I could use that for other problems and just solve it more quickly. Where I use ANSYS as my stepping point. And sometimes it's the opposite, where I come up with, a lot of times it's the opposite, where I come up with an approximation using Excel, and then I use ANSYS to get the exact answer. There was one case where I took a look at it was a cylindrical system, and I wanted to better understand what could cause deformation. So I came up with a formula that I thought worked, and then I did a little design of experiments within ANSYS. So I changed, I double thickness, what happens? I double the radius, what happens? I double the pressure, what happens? Etc. Just to validate my formula. So sometimes I do that.
Okay. Yeah, it seems to me like there's an opportunity here to build kind of you're building your own repository, but have something more kind of online that can be shared across the community.
Yes.
There seems to be an opportunity there. Okay, let's go to this question here, and let me read the question. It's from Mohammed. I can't really see the El Sayed. I'm sorry if I'm mispronouncing your name, Mohammed. So what behaviors can be considered first order, second order, third order effects? And because Andy, in some videos you do mention that. So do you want to talk about what you consider first order effects, second order effects, third order effects, and you can give examples.
Yeah. So I use that term kind of loosely. And the way I've considered it is when you go back to, oh gosh, I don't know if it's differential equations or whatnot, but like when you solve for the heat transfer relations or other even structural relations, you come up with approximations to the Taylor series, and then you can say that, oh well, this is order of 1 or order of 2, and you can come up with varied approximations. A good example is if we have, I don't have any examples around me right now. Maybe I'll just grab something that I can touch. So like, assume this is a beam, and then I apply force against it. Small angle approximation says that for 5 or maybe less than 15 degrees, the sine of 15 degrees is a small number, or the cosine of 15 degrees is approximately 1. So therefore, you can say that the deflection is equal to FL cubed over 3EI. Now, as this deflection increases, that doesn't become as valid, and you hit a second order effect because you actually have some other effects going on. One being that this thing is under tension instead of just being under pure bending. You might have some shear effects. So I use that term kind of loosely. When people think of second order, they're thinking okay, quadratic or third order cubic. So like if you solve the formula, I can tell you that when it comes to catenary beams or lines, that's like power lines that kind of droop like this. That involves a second or third order solution in order to get the proper deflection from that. And then one can, there are physical problems where if you want to get the exact answer, it's kind of like an x plus x cubed over 3 factorial plus x to the 5th over 5th factorial kind of thing, where the more places you have out, the better the approximation you can get. So said another way, first order approximation is a quick hand calc in my vocabulary. Second order is if you want to get a slightly closer answer, you start including more and more effects.
Mm-hmm.
And that's all I would read into it. It's certainly physics is beautiful. Like when you go deeper and deeper into it, you learn that there are other interaction effects. Like if you do the full equation out, with this beam bending, you do have shear effects. And so if the length to diameter is smaller, then you have to include more effects in order to get the true answer.
Okay. Let me go to this question from Sam. What programming languages should a mechanical aerospace engineer learn to use advanced user-defined features in ANSYS or any analysis software? So, in fact, I will kind of expand on this question. It comes back to something that we're dealing with in education, because I did my PhD, developing my own kind of unsteady Navier-Stokes code, and God forbid, Fortran. But now I'm like completely, my work is all kind of ANSYS based, and I'm not using really a lot of the programming skills except for when I'm going into, say, doing some user-defined functions and so on. So maybe I'll turn this over to Sean. It's like there are two things here, right? One is if you want to become a power user of ANSYS, okay, how do you go about it? Second, how important is learning a programming language now if you are, if you're going into this kind of an area?
Right, those are great questions. So, having a background in coding does help, because there are going to be times when you can really leverage that. For example, the course that you were teaching was concentrating on ANSYS mechanical, right? But the foundation of that was the
also. Yeah, we did have both FEA and CFD there.
Oh yeah, and then what I was going to say is the MAPDL language is what actually is running behind the scenes, and that's just an interpreter scripting kind of language, which is not very structured. Power users of ANSYS will know the language. So what I would say to people is, if you've already started to master mechanical and you feel comfortable in it, then what you want to do next is dig down into, you open up the right-click on the solution folder and open up the solver file directory, and there's a ds.dat file. That's actually the file that has all of the commands that are going to be interpreted by the solver. So even when we hire someone in, we may get someone who is very good at using the GUI but doesn't have that foundation. When we find engineers that know that code, they are very plug and play, in the workforce and companies that are looking for ANSYS users. So I would say, to be a power user, you don't have to know a coding language, but most of us should know, understand the logic and the flow of a software language. Now, the ones that are commonly used in ANSYS, the user subroutines are very advanced. So if you want to write your own, let's say, user material, you're still going to need Fortran. There are ways to get around it. It's not very trivial, but knowing, C or a variant of C, an object-oriented programming language, would be helpful. Fortran. And then the other thing is, a lot of our tools now are scripted through Python. So if you want to do some really fancy scripting and changing the GUI and doing things like that, then you can go ahead and learn Python. So between Python and Fortran and C, those are the common ones. As far as my knowledge on the mechanical. Now on the fluent side, I'm not as aware of which language is unfluent.
Okay, and then there are questions about, okay, I want to learn about vibration, or I want to learn about crash. How does one go about that? So obviously you have a customer who comes with, say, they're doing some crash testing and so on. And what kind of training materials do you give them access to? And how can somebody you know, say at a university who doesn't have access to your expertise or your team's expertise, kind of, you know, can they be self-taught?
I would say they can be self-taught. Instructor-led is definitely a big benefit. But if it's at if it's at a university, then the professors at the university will have access to all of our training material and what we consider our solutions. So we create lots of tutorials. Our database of what we'll call knowledge materials will be at 10,000 by the end of this year. And those contain cases, all different kinds of cases. For example, I wrote one on bolt modeling. Bolt modeling is, ubiquitous in the industry, and we get 5 questions a week on bolt modeling. So we have a very nice tutorial that goes through all the different ways of idealizing a bolt, from a beam to a solid, to including the threads, to not including the threads, to all the different ways of doing something like that. So if someone wants that kind of information, the internet is a great source. There is a lot of YouTube sites available. There are people who have published the information, freely available. But at the university that has ANSYS, then they'll have access to some of our training material and our tutorials, etc.
Okay. And I should mention that I'm trying to build SimCafe.
And SimCafe, yeah, I should mention that.
.org as where you can. I mean, the MOOC itself, the course itself, I envision it as this is where you build your fundamentals and how you need to think about it, and then further learning. The ANSYS training materials that for instance, students in the university can get access to through their professors who are connected with ANSYS, or who is a licensing representative. That material is useful, but I'm also hoping to scale up the material on SimCafe so that users can also contribute material to it, and so that becomes, I think there's a lot of opportunity there in terms of people teaching each other. Okay, let me see. I'm just scanning through the questions. I think most of these we have addressed. Let me pick this one and make it a little bit more general. So Damal, or Fabrice from Mauritius, he's asking about, how to define the general governing equation for complex simulations, as, for example, a helical vertical axis turbine set up in a pipe, and determine the speed of rotation, and etc. And I want to make this a more general question because I see this students dealing with this all the time, and I tried to give a sense of this in Module 3. Is you have this really complex application, right? How do you kind of approach it? So let me turn it over to Andy first. You kind of indicated how you went about it for the bolted flange, but if you want to talk more about it, because you always have to reduce it to something more tractable, right? So what kinds of thoughts are going through your mind?
Sure. So the first thing is that, that's an exciting problem, I just visualize what's going on. So I visualize what's causing the rotation, where's the energy coming from. So if it's a gas turbine or electric power that's causing this thing to spin, I imagine the energy going from the coil to cause rotation, and then as it spins up, you have omega double, or I guess you have theta double dot, the acceleration of this shaft, and then it's attaining a certain velocity, and then as it's spinning, what kind of forces, if I was just kind of floating around on there, and if I was just an atom that was merely passing across, what would it feel like? So there's drag along the maybe the shaft, but maybe it's not that much, but along the blades, and then so there's that counterforce acting on it. There's the counterforce acting from the magnet, so I visualize those things, and then I write them down, or I just kind of draw them on a free body diagram, and then there's some governing equations to show how things work. So if it's a mass spring damper system, it's just mx double dot plus bx dot plus kx is equal to some forcing function. Or for structures, it's a little bit more simple. And then I like to draw it out and do a free body diagram. And then the other thing that I look at is, now that I visualize this, what am I looking for? Am I looking for when it breaks? Am I looking for, what's the exact question I'm trying to answer? If I'm looking for when it breaks, then I visualize the ways that it can break, because there may be multiple. And then I try to attack the problem from that. And because the problems can be, because like these systems can be complex, I have to kind of I have to simplify the problem to say, well, if it's like a transient thermal problem where we have varying temperatures across the structure, I may simplify it to say, well, worst case, everything is 1,000 degrees Celsius. And then this is what will happen if everything was that temperature. And then I start off with like a rough answer, and then I kind of break it down smaller and smaller. Like if I was at a restaurant and I was waiting for my meal, if I took a pen and I only had the small napkin to write on, and I had I wanted to come up with an approximation of what happened, I would challenge myself to figure out how do I predict what would happen on the small piece of paper. So that would start, and then that piece of paper may turn into a few pages.
Okay. So we have about, a few minutes left. I want to end in about 5 minutes. So let me turn it over to each of you. Parting words to students who are going through the course. I'll start with Andy and then Sean. And last but not the least, I'll go to Julio and, talk about his impressions being a TA and learning ANSYS, so that we end with the student perspective, which I think is, is the most, this is what is all exciting about, helping people kind of learn, share this knowledge. And I know both of you, Andy and Sean, you are very, very interested in that aspect too. Not only about, becoming kind of power users and experts, but also sharing that knowledge. So it's been really a pleasure working with both of you. And so let me turn it over to Andy first. If you have any parting words to...
Sure, yeah. I'd like to thank all the students for participating. I think this class is awesome. It's really well put together, and I think it's great that everybody is so willing to learn and continue to learn. I've had a lot of people connect on LinkedIn, and it's just really exciting to hear everybody's stories, because it's like, wow, this world is really going to become a great place in a few decades with all the work that we're doing. I would encourage people to keep reading books. Like I read a textbook a quarter. It can be difficult, however, it's important. The world needs this. And if you're feeling overwhelmed by analysis, just start with small steps and then build up. And if you're feeling underwhelmed, then step on to some bigger challenges.
Okay. Thanks so much for all the help you have been providing for developing the course, Andy. It's been just I've learned so much working with you, and it's been I just love the online medium, because now when like talking about interpreting results from the bolted flange, I was like, students need to hear from Andy directly, because I don't have that knowledge from industries, and to bring you in right when they're learning the thing is just fantastic about this media.
Sure. One thing I forgot to mention earlier. So this is the CFD question that I got earlier. So good results come within 20%. Sometimes it's okay to get a result within 100%, because if the delta pressure is really small, maybe it doesn't matter. And if you're within a factor of 2, you may be fine. So that was just a little going back on that. Thank you.
Yeah. So basically, engineering judgment, right? You need to have good simulation skills, but the engineering judgment is like critical.
Yes. It comes with practice and failure.
And Sean, parting,
Yes.
Thoughts and words.
I would just couple things. One, if you're in this chat right now, that means you've gone through a lot of this material. So congratulations to you for making it this far, and it sounds like you're interested in this. So pat yourself on the back for doing that. Sorry, we won't be able to answer all the questions. I guess Rajesh will discuss putting on my tech support hat, I see these questions coming in. They feel really bad. They're not all getting answered. So, I won't take the words out of Rajesh's mouth, but I'll let him fill it in. But we want to discuss that. But I would also say,
yeah. So let me just chime in here.
Yeah.
Sean, sorry to interrupt you. We will, we look through the questions, and if Sean and Andy want to respond to any of those questions, we will, we will add it as a PDF to the to the page.
Okay.
I think Andy has to leave, so thanks, Andy. Thank you.
Thank you.
Yeah. Thanks, Andy. And I would just, Andy kind of alluded to this, and I would say what you want to do is take the, what we call the crawl, walk, run approach to any problem. So, that would be one of my recommendations. We see a lot of people who dive in head first, and sometimes it's students and sometimes it's our commercial customers, but they want to model, it seems like, the entire system, and they haven't even taken the time to understand a part of it. So what I would say is this: if you're running a model and it won't converge or won't solve, break it down into smaller pieces. Take out the complexity. Start off with, constraining it. There was a question there about, my frictional context won't work. I went to bonded. Add complexity in little by little. Don't try and get it all in at one shot, and that will go a very long way to being less frustrated with FEA, especially nonlinear FEA, which can be very, very, complex and time-consuming. So, yeah, I always tell people, do the crawl, walk, run, and double check your results against either a hand calc or look at your force balance or something before you go into a meeting and say, this is the answer.
Okay. And thanks very much, Sean, for joining the call and for all your help in
thank you.
In developing the course and SimCafe and so on. And look forward to continuing work together.
Absolutely.
Okay. And let me end with the student perspective. Julio, do you want to say something about your experience with the course and with learning ANSYS?
Yeah, so my first contact with ANSYS was about 6 months ago, taking classes with Professor Bastron. So I revisited all the material on the MOOC, and after that I started to take the tutorials in SimCafe, which is a great resource for the learning, and they're amazing. I learned a lot. I'm more into CFD than FEA, so I've taken mostly every tutorial there, and I feel that I'm more prepared now in CFD, and also writing some tutorials there in case you want to learn some more about vertical axis turbines. And taking what Sean said, the learning curve is very steep. You can learn pretty fast the basics, and when you start to dig into the more complex things, you get very excited. And what he said about starting with simple things and building difficulty little by little, I learned that very, very much now. It's very important to do that.
Okay. Okay, so thank you everybody for joining us on this call, and hope it was useful, and see you in the course.
Thank you.
Thank you. Thanks, Julia.
Thank you.
Thank you.
Thanks, Sean.
Thank you. Bye now.
Bye.
Bye.